So okay, let's take a look at this example. So here we like to introduce the idea of surface integral. And as usual, the surface integral of complicated surfaces, complicated curvature surfaces can be divided into small planes, small surfaces. They should be so small that the surface can be regarded as planar surfaces. And if this assumption is valid, then the surface integral can be done more simply in terms of mathematical calculation. So for the figure shown, you see curvature surfaces, and it has been divided into 16 smaller surfaces, and each surface may have different orientation. That is, the normal direction of individual subsurfaces is not exactly the same. Nevertheless, for these 16 subsurfaces, smaller surfaces, they can be regarded as planar ones, so that they can have a uniform orientation within that region, which can be represented with normal vector. And the calculation of the field passing through the surfaces, again, the amount of the field passing through the surface is calculated in terms of scalar product. So only part of the field is accounted. Only the field that is in parallel with the normal direction of the surface are counted. Only that part is counted. And if the field is tangential to the surface, then that part of the field is not accounted for surface integral calculation. So you need to be sure, need to be careful about the geometrical relationship between the field and the orientation of the surface. And finally, the effective field calculated in individual regions can be added up to find the total sum of the field that is crossing the surface effectively, right? So for the figure shown in the previous slide, we need to calculate the angle between the field and the normal direction of the surface individually, which is referred to as alpha j here. So j, the subscript j stands for the index of the surface. Alpha is the angle between the normal direction of the surface and the direction of the magnetic flux B. So here you see ANJ and BJ. The angle between ANJ and BJ is alpha j. All right, and the product of magnetic flux density and the surface, that is B delta S cosine alpha, which is shown in equation 2.7. The product of B delta S and cosine alpha is the so-called magnetic flux. So you must have noticed that B is referred to as the magnetic flux density, okay? And delta S is the area. So the density times area becomes the units of meter square cancel out. So you have the physical quantity of magnetic flux, which is labeled as 5 in electromagnetics. 所以 B 是磁通量密度。那磁通量的话，通常是写作大写的 Greek letter phi。OK， 是大写吗？这是小写，对不起，这是小写。Greek letter phi。So this is the contribution of the total magnetic flux, which is phi, can be calculated from individual phi that is passing through small surfaces. That is delta phi j. The delta phi j is the magnetic flux passing through a small area, delta S. Okay. So the total magnetic flux phi for this curvature area S is the summation of delta phi 1, delta phi 2, delta phi 3, and etc., which is the product of B1 cosine alpha 1 delta S1 plus B2 cosine alpha 2. Here's a typo， 有没有看到？15年来我又找到一个 typo 了 ，OK 哈。这是我自己打的还是课本抓下来的 ？alpha 2对。课本上有没有这一个是有没有这个equation？啊，天哪，大家都没有课本哦，好吧？哦，好，没关系了，哦，反正这个是 alpha 2了哦 ，OK。Right, so it can be written as the summation of bj cosine alpha j delta sj, and so it's actually the scalar product of the two vectors. So that's the expression for the calculation of magnetic flux passing through an arbitrary surfaces. So if we use the concept of infinitesimal surface vector, then the calculation or the summation can be written more directly as the scalar product of bj dot delta sj. Okay, so you directly you use the concept of scalar product to represent the calculation of effective magnetic flux passing through an infinitesimal surfaces. So here is an example, a numerical example. So here we have a relatively strange expression for the magnetic flux density B as 3 times x times y to the square, and is oriented to the z direction. Well, in practice, you probably don't have this kind of magnetic flux density distribution. But anyway, this is just a numerical example. So let's accept that B, the magnetic flux density, can be expressed as 3 times x to the times y to the square in z direction. And you are trying to calculate the amount of magnetic flux crossing a region spanned by 0, 0 to 1, 1. Okay, so so for this simple example, the orientation of individual small surfaces are the same. They are all aligned in the z directions. Okay, so in fact, even though that this surface is divided into 25 smaller ones, their orientation are all the same, which is z direction. Z direction. And for the simplicity of mathematical operation, we use the center of each small pieces to represent the coordinates of this small region. As the center, you use the center point coordinate to represent the location of this small region. Well, this is only one approach to describe the position of this smaller region. It's you do not have to choose the center point. In fact, you can choose anywhere in this region, say the top left corner or bottom right corner. It's all the same as long as you have a fine grid. 我这边要讲的事情是在这个 example 里的拉用中心点，看起来是合理的嘛，对不对？但事实上是随便，你不一定要选中间点，你选任何一个 corner 或者是 你可以自己定一个规则。但这一种计算也就是积分的计算，或者是说数位化的积分计算，它漂亮的地方就在于说，你这个规则其实没什么太大关系，只要你切得够细，答案都是一样的。好，所以你们大概，我希望你们了解这一点 ，OK 只要切得够细，其实你选中心点或选任何一个角落都是一样的结果。Alright, the reason why we need a point to represent the location of this small region is because the magnetic flux density is not the same in this small region. Okay, so as you can see here, it's described as 3 times x times y to the square. And the coordinate of the location within this small region are not the same. So the field, the magnetic flux, is not the same in this small region. Nevertheless, as the region becomes smaller and smaller, the difference in terms of magnetic flux density doesn't matter. They will approximate to a constant value. Okay, so even though with this relatively coarse grid, coarse 是什么？粗略的、粗的、比较粗分的哈。With this coarse grid, you may expect certain error. Nevertheless, as the grid becomes finer and finer, the error due to quantization can be minimized. Can be brought down to nearly zero. All right? So you can substitute the expression for the coordinate, that is the center of the surface, into the expression of the magnetic flux density. So you use this value and you think, the magnetic flux density is about the same, is nearly uniform within this small region. All right? So so this is the expression for your magnetic flux density in a specific region, and the size of the small region is constant in this problem, which is the product of 0.2 times 0.2, which is the length and width of the region. So the differential surface delta S is constant, that is 0.04 AZ. As we have seen in the previous slide, that in this surface on the XY planes, all the smaller divisions, all these divisions are oriented to the positive Z direction. All right, so delta Sij is a constant as 0.04. And the direction is AZ for OI and J. And because we only divide this area into 25 regions, so the surface integral can be carried out in this equation. So as you can see, it's equivalent to taking line integral twice. So you first taking the line integral along the x direction, and then taking the line integral along the y direction. So you kind of taking the line integral twice. Okay, and there's another way to interpret this interpretation in this calculation is that you loop around the 25 regions and calculate the magnetic flux. The magnetic flux accumulated in all 25 small regions. And note that this is a scalar product, so only the Z component counts, because the magnetic flux B is oriented toward the Z direction, and the normal direction of delta S is also Z direction. All right, so you just carry out this computation and end up with 0.495. And of course, you know that surface division is somewhat coarse. It's not fine enough. So you should expect some error. So what do you think? If this value is higher or lower than the actual value? Well, I don't know. So to find out, you can carry out the integration in a more conventional way. All right? So equation 2.12 provides you the orthodox way of carry out the calculation. OK， 我刚才讲了一个比较有水准的字啊 ，orthodox， 什么意思？orthodox 指的是那个基本教义派啊。orthodox 基本教义派，所以你只要在政治，你只要去留意政治新闻的话，你就会听到有人讲说那个什么以色列的那个基本教义派，orthodox是那个戴黑色高帽的那一种留辫子的那一种那我们叫 orthodox。所以你也可以把它形容成比较传统的一种做法那当然就是你平常正常学的微积分嘛OK all right okay so the conventional way to carry out the surface integral is to divide the surface into infinitesimal small regions. So you use the conventional calculus symbols to do the surface integral. And as I already mentioned, the surface integral is in fact a double line integral because a surface is expanded by two differential lenses. So the computation of the surface integral is in fact relatively simple. So because the expression of B and ds can be found exactly as 3xy to the square az dot dx dy az. So the integrand to be integrated is 3xy to the square dx dy, and so it can be the surface integral is can be carried out in this fashion. So this is referred to as the analytical solution. 然后我们再学一个字我不知道你们有没有学过 analytical solution 这个字就是叫中文叫解析解啦也就是用微积分硬干出来的解叫 analytical solution OK。那刚刚的那一个切成25块的，我们就叫 numerical solution so it's an approximated solution. However, in modern day engineering, the numerical solution can approximate analytical solution with the assistance of computational power. All right, so we see the integral, the actual integral of this problem is 0.5 Web. So the difference is about 1%, which may be acceptable in terms of accuracy. All right. So next, let's move on to the another idea about surface integral. That is the so-called closed surface. What is a closed surface? A closed surface is a surface with no edge. So say here is a piece of homework written on piece of paper. So of course the surface of the paper is a surface. Is that a closed surface or open surface? It's not a closed surface because you can see the edge, right? And the surface of the bottle. The whole surface of the bottle forms a closed surface. So you don't have edge. Edge. Okay. Sometimes some problem, some conventional astronomy problem is that does the universe has an edge? or not? Or about 500 years ago, if you sail on the ocean and you go further and further to the west or further and further to the east, most of the people on that day will think that it will eventually fall down to the first out of the earth because you are crossing the edge of earth. And unfortunately, or fortunately, the earth is actually a closed surface as a sphere. Okay, so you won't fall down at the edge of ocean. All right. All right. So here is the concept that I need to notify you is that for this surface, how many directions is the surface? Well, actually, if you are talking about the normal of the surface, you have two answers. One is pointing to the front, and the other is pointing to the back. And how about the closed surface? What is the normal of a closed surface? Well, for closed surfaces, according to electromagnetics or most of the engineering textbook, for closed surface, the normal direction is pointing outward. So you have only one direction, or at least one positive direction. So the positive direction of a closed surface is pointing outward. Suppose that the origin can be enclosed by this closed surface, then the direction of the closed surface is pointing outward. All right? Unfortunately, we are not in a class of topology or some high-end mathematics class, so we won't encounter very complicated geometries. 所以还好，我们在电磁学里头，至少到目前为止不会碰到太复杂的立体几何结构了所以大概就是一个圆筒啊，或一个圆球之类的东西所以它的那个所谓的面的方向是容易定义的嘛就是朝外吧 ，OK alright so whenever a closed surface integral is evaluated, the unit vector normal to the differential surface are chosen to be pointing out of the volume. So that's what I mean outward. So as to give the outward flux of the vector field, unless specified otherwise. So let me make myself clear. That is, if we have a closed surface, like a sphere, okay, use your imagination. And if you have, for example, if you have some positive charge Q placed within this closed surface, then of course, you can draw the E field due to the presence of positive charge. Then the flux of electrical field is across this closed surface is a positive number or a negative number. Well, according to the definition, the positive flux is pointing outward. So if the charge placing within this spherical closed surface, then the collection of electrical field is a positive number. On the other hand, if the closed surface, if a negative charge is placing within the closed surface, then the flux, the summation of the flux of electrical field due to electrical field is actually a negative number for negative charge. All right? So that's the difference. Okay, so be sure to remember the definition of closed surface integral. And here's an example. So suppose we have a strange magnetic field, magnetic flux density description like that. Well, it's legal, even though that you may not encounter such kind of magnetic flux distribution in real life, right? But, well, it's legal. So B has three components in the x, y, and z directions, and in each direction it has some strange dependence. They are, the x component bx can be represented as x plus 2, and the y component is related to 1 minus 3y, and the z component is 2z. And when we want to calculate the flux flowing out of a cubical box enclosed by the origin and point G, which has a coordinate of 1, 1, 1. Okay? So as shown in this figure, you have a cubical region of a cubical volume, and a cubical volume have 6 surfaces: the front, the back, the left and right, and top and bottom. So they can be written as the sum. So if you want to calculate the magnetic flux flowing out of this cubical region, you can decompose it into summation of the 6 surfaces, like this. So, and what to do next? Well, you carry out the surface integral on the 6 surfaces and add up the result, right? So you notice that the 6 surfaces are the front, the back, the left, the right, and top and bottom. And their directions are different. For example, when you consider the surface enclosed by point E, F, G, H, which look like at the front in this plot, what is the direction of plane E, F, G, H? What is the direction? What is the normal direction of this surface? It's positive x, positive x. On the other hand, if you are looking at A, B, C, D surface, is the normal of A, B, C, D is pointing toward negative x direction. So for G, F, B, C, it's pointing to positive y and negative y, positive z, and negative z. Okay, so all 6 surfaces have different orientations. All right, so you need to, so when carry out this integral, this surface integral as 6 smaller pieces, you need to be careful about the coordinates. For example, for surface ABCD, which is pointing to the back, as we see from this figure, the x-coordinate equals to 0. X-coordinate equals to 0, which is a constant on this surface. So the B, the magnetic flux density expression is simplified like this. Because x always equals to 0 on these surfaces. And while y and z are both variables on these surfaces. So the integral on these surfaces, which is b dot ds, can be carried out by substitute this relationship in this expression. Note that the calculation is not quite difficult. It's relatively simple because what? Because ds is minus ax direction, and therefore the y component and z component in the expression for b doesn't count. Only the s component counts. So s component of b on that surface is 2. So is simplified as minus 2 dy dz, and you take in the integral along y direction and z direction, so it's just minus 2. So you can do the same for other surfaces, and for example, for the front, which is EFGH, the surface integral is 3. And if you calculate the integral for the left, it's minus 1. The calculator of the right is minus 2. And for the top surface is 0, and the bottom surface is 2. Then, to find out the total result of this surface integral is this. Minus 2 plus 3 minus 1 minus 2 plus 0 plus 2, and it equals to 0. Then you say, well, is that a tricky problem, or what is the physical interpretation of this result? The physical interpretation of this result is that this demonstrates that the magnetic flux density provided in this case is legal. 它是一个合法的磁通量。它是一个合法的磁通量。Well, because we haven't started talking about Maxwell equation. Actually, the fourth equation of Maxwell equation is referred to as Gauss's law of magnetic field. Okay, let's practice about the Maxwell equation. Maxwell equation, as I guess you already know, you have 4 equations. The first one is Faraday's law. The second one is Ampere's Kirchhoff law. The third one is Gauss's law of electrical field, and the first one is Gauss's law of magnetic field. Ah, 这个是法拉利定律第一条。我为什么要从第一条开始写嘞？因为我忘记下面那2条了。写一写，说不定我就会想起来。想起来了 ，OK， 好。All right. So what we are looking at is the Gauss's law of magnetic field. So as this equation suggests, for any magnetic flux density distribution, if you perform a closed loop integral, it must equal to 0. What is the consequence of this result? The consequence or the physical implication is that 意指的那个意思，然后 the physical implication of this equation is that there is no standalone magnetic charge. On the other hand, if you look at Gauss's law of electrical field, it says if you calculate this is the electrical flux density. if you calculate the electrical flux density of a closed surface, if it is non-zero, then it suggests that there is some electrical charge placed within this closed surface. So rho is electrical charge. 我写错了，对不起。Rho is electrical charge density, and here we are talking about electrical charge, so it should be replaced with Q. Okay, so we do have electrical charge, right? So the closed surface integral around the electrical charge should be non-zero, and depending on the polarity of the charge, which can be positive Q or negative Q, the flux can be positive number or negative number. All right. So if I have a problem to ask you to calculate the magnetic flux density around a closed surface, and the result of this calculation is non-zero, then it suggests two cases. One case is my problem is problematic. Okay, I have the wrong problem. The second scenario is you didn't do the math, do the calculation correctly. All right. So for any legal distribution of magnetic flux density, the closed surface integral must always equals to 0. So we happen to look at one example about the fourth equation of Maxwell equation. All right. Okay, that should